dopo la facciamo. Allora noi ci vediamo così. Devi stare sì, la zona.
Aspettiamo il direttore.
Il direttore vuoi che dà un prova da un piano?
Se no io comincio.
No, faccio io ormai, ma aspettiamo
5 minuti. Intanto non parlo tanto, mi guardi.
Sì, che ore sono adesso?
Le 11:05.
Però massimo è 4 per cominciare.
Sì, no, aspettiamo le 11:08 e poi iniziamo. E hanno visto tutti lo streaming, quindi praticamente secondo me tanti vogliono guardarsi lo streaming.
Caterina, io lascio fatta questa classe qua. Sì, non si diventa che non c'è se ci sono problemi di
Sì, Martina è stata bravissima.
Ma se l'audio si sente come prima,
Adesso lei fa un attimo
se è un problema loro,
ma aspettiamo ancora 2 minuti.
Stai nel raggio del microfono?
Sì, aspetta che tolgo questo dal raggio del microfono, che fa brutto. Poi che proviamo? Provo. Sì, mi sembra che tento di parlare forte.
Senza microfono? Ah, ok.
Allora finisce all'1. In teoria, l'ultima mezz'ora sono domande. Sono 6 presentazioni a 10 minuti l'una, quindi molto precise. E sono
Poi
piuttosto...
ogni tanto farò vedere a un certo punto alle 12:30 vengono liberati i video.
Magari la liberatoria la compiliamo alla fine.
Come? Sì, passo dopo dall'ufficio?
Sì, io sono giù in portineria.
Ok, sì, passo dopo. Sì, perfetto. Come se fosse firmato. C'è un po' di gente.
Vuoi che dica no?
Aspettiamo un minuto.
In italiano? Una in italiano.
Italiano per piacere.
Tu adesso parli in inglese?
Tu probabilmente non fila. Di che siamo questi?
Sì. Allora, benvenuti, grazie di essere qui. Poi verrà anche il nostro direttore Massimo Turato appena riesce a liberarsi. Adesso Rosanna Sordo ci farà una breve introduzione della missione Gaia per rinfrescarci la memoria e lo farà in inglese perché ci sono qui diverse persone che capiscono bene l'inglese. E alle 11:30 inizierà la conferenza stampa presso ESA dove ospite Antonella Valenari e dove parlerà anche Antonella Valenari e noi sostanzialmente guarderemo anche lo streaming appunto di ESA. Però Rosanna è qui per commentare ogni tanto, se ci sono domande fatele pure, non è che stiamo qua a guardare tutto il tempo lo streaming così. Se c'è bisogno anche di commenti, di passare dall'inglese all'italiano, fallo, anche perché siamo seguiti in questo momento via streaming da diverse persone, anche da studenti, quindi cercheremo di passare un po' dell'inglese, ogni tanto l'italiano e soprattutto di passare dallo streaming a qualche commento live. Se qualcuno ha domande poi io cerco di seguire anche le domande che fanno in streaming, casomai. Grazie Rosanna.
Allora, thank you everybody for being here with us for the first data release of Gaia. The main event will be the streaming of the Gaia Press conference in ESA, starting in 20 minutes more or less. It will consist of 6 presentations, 10 minutes each, very focused and concentrated on different aspects of the Gaia mission. They will give you all the numbers of the details of the data release 1. My purpose here is to give you, remind you what is Gaia. Because Gaia is well known, but the data release 1 is not Gaia. It's different in several aspects, and you need to be aware of this. So, Gaia was launched at the end of 2014, nearly 1,000 days ago. And it worked since the first month to collect data. Gaia is scanning the entire sky several times repeatedly. It will do it for another 4 years, and 5 years in total, pending an evaluation of the extension of the mission. At the end, it will provide the Gaia final catalog that will contain, down to magnitude G 20.7, around 1.2 billion sources. For all of them, it will give photometry, astrometry, and many other quantities that I will give you here. So photometry in 3 bands, G, BP, and RP. G is more or less white light covering the whole optical range. GBP and GRP is the same, divided in 2 to give the color information that is needed by the astrometric instrument to have the correct for chromaticity effect and derive precise centroid of the image, and to allow for the precise astrometry that is the key goal of Gaia. Astrometry, meaning position, parallax, and proper motion down to magnitude 20.7 at micro-arcosecond level, while the photometry is the millimag level, which is exquisite and accurate. We will not have radial velocity down to this phase magnitude, of course. It will be limited at the brighter end, and I will talk about it now. For all the sources, you will have the spectral energy distribution covering the whole optical range, very low resolving power, very low photometry-like, but very high accuracy, 1-2% flux level. And you have the variability information, both astrometric and photometric, for all the sources at the end of mission. The variability information is useful right now because there are science alerts for alerting for supernovae, for follow-up or special events, and it is already. The variability information is useful right now because there are science alerts for alerting for supernovae, for follow-up or special events, and it is already active and productive, so to speak. All of these stars are unknown in principle because there is no existing catalog of them, so you don't and productive, so to speak. All of these stars are unknown in principle because there is no existing catalog of them, so you what is a given source. At the final catalog, you have a classification of the sources as star, galaxies, quasar, and you don't know what is a given source. At the final catalog, you have a classification of the sources as star, galaxies, quasar, and object, and so on. But you will have an astrophysical parameterization of all the sources according to their type. Certain parameter for stars, certain other for solar system object, and so on. But you will have an astrophysical parameterization of all the sources according to their type. Certain parameter for galaxies, and so on. For the bright star, brighter than G17, sì.
Faccio solo un annuncio a mattina.
Other for galaxies, and so on. For the bright star, brighter than G17, sì.
Faccio solo un briefing, mi dicono che è a Santo Giorgio.
Prima è arrivato il direttore. Abbiamo cominciato perché sennò non ce la facciamo.
Un annuncio a mattina, lo streaming mi dicono che è a Santo Giorgio.
Prima è arrivato il direttore. So G, more or less G is equal to V, so to speak, except for the extreme color stars. You will have the radial velocity derived from. Okay, for the bright stars, G, more or less G is equal to V, so to speak, except for the extreme color stars. The spectrum on a short wavelength range around the calcium triplet line in the infrared. With the spectrum, you will have a more accurate astrophysics. You will have the radial velocity derived from the spectrum on a short wavelength range around the calcium triplet line in the infrared. Parametrization, temperature, gravity, metallicity, and some other chemical information if the star is bright enough. Using 14 with the spectrum, you will have a more accurate astrophysical parametrization, temperature, gravity, metallicity, and some other chemical information if the star Gaia, the DPAC, the Data Consortium and Analysis, the Data Processing and Analysis Consortium, is ready for the first data release, which is not the final catalog. Using 14 months of observation, Gaia, the DPAC, the Data Consortium and Analysis, the Data Processing and Analysis, you will have the same number of sources, but we will not have the same amount of information. Okay. Simply because 14 months of observation are not enough to disentangle the motion, is ready for the first data release, which is not the final catalog. You will have the same number of sources, but we will not have the same amount of information on the motion of the star. You have degeneracy, and it is fairly impossible to derive an astrometric solution with only 14 months of data. So we did a trick. Okay. Simply because 14 months of observation are not enough to disentangle the motion of the Earth from the motion of the star. You have degeneracy, and it is fairly impossible to add the information from the Tycho catalog. For 2 million sources, this is a density map, a source per square arcmin in the sky. This is all the data release 1 catalog, compiled only from the data Gaia data. And you see clearly the stripes artifacts due to the incompleteness of the measure. The incompleteness in the coverage of the sky, 14 months are not enough, and some gaps due to something that could be problems in the software that had to be resettled. The contamination by ice, we suffered from ice contamination in the first month of the mission. You have meteorites hitting the instrument. Some of them are very minor, some of them you see small chunk in the small movement in the astrometric measures. And some of them were big, and the data had to be couldn't be calibrated. You will be calibrated in the next data release, but not now. So this is to say that your favorite source might not be in the data release 1. Just an example, Hipparcos catalog consists of 118,000 stars. In the data release 1, you have 93,000 stars from Hipparcos catalog. This is particularly severe because Hipparcos stars are bright, and the bright end of Gaia is especially difficult to calibrate because of saturation. It will improve in the next data release, but you have to be aware the sum of the stars that you are looking for example, or galaxy or whatever, may not be in the data release 1 due to problems in the calibration. If the error in the quantities that we want to provide are too high, or the correlation with other things are too high, we simply do not publish them because it's worthless to do that. So we have an embargo that will came down in 1 hour, more or less. And all the data will be available from the ESA Data Archive, which is the first link here, and from Mirror Science Data Center, CDS, but also the ESA Data Center in Rome. And the user interface is the same for everybody, in my understanding, and there are, it allows for very basic query or more complex in SDSS style. You need to use databases to be able to really use the Gaia archive. And the cross-match with several archives available is provided because it's very tricky. The precision in the coordinates of Gaia is so high that you are in real trouble in doing it by yourself without taking into consideration the correlation between the coordinates, the errors, and the very lower precision of all other catalogs available in literature. You have, of course, Hipparcos and Tycho, Zumas, SDSS, you have RAVE, of course, because they are Hipparcos data. You have many other astrometric survey. Everything is available there. Data release 1, we couldn't publish the data without the documentation. So there is a huge amount of documentation available online since in an hour, more or less, and from the ESA portal. Tomorrow there will be 5 big papers describing the whole mission, the first snatch, the first data numbers on data release 1. And then you have the whole list, this list of papers that will be published in a special edition of Astronomy and Astrophysics. They are not accepted yet. They will be in the next days. And they are part of the data release 1. There is an electronic version that will be updated with everything. Everything you need to know is there. All the information must be there, otherwise we couldn't publish the data release. So in a few minutes, we will connect to ESA for the public event, official data press release. You will see 6 presentations focusing more on the numbers of the data release 1 and different aspects, from the astrometry, on the precision of the astrometry, on the photometry of sky, the view on the clusters, and the effect, the impact of DR1 on the distant ladder. There will be at the end a session of question and answer, but I'm here in the beginning, or if you don't have time to say here, I'm here if you have some questions. We have 10 minutes more or less before the connection. This is all I have to say. Thank you for being here. Ok, non ho detto moltissimo di Gaia perché tutti i numeri sarebbero troppo.
Caterina, sono lecita a dire...
Se vuoi, sì. Devi andare lì dove c'è Rosanna perché così ti vedono lo screen.
Ah, ok.
Qua. Ah, sì, qui. On the spot.
Well, Caterina asked me to say a few words. Well, I cannot speak about the science because, well,
No science.
I don't know anything about the mission. Actually, I know because I am partially involved, but not as much as our colleagues. For us, it is an important day because the Observatory of Padova and the university are deeply involved in Gaia. We have at least 2 persons fully involved in Gaia permanently. 3 persons. Well,
Francesco there.
Tristan,
PhD.
PhD student Francesco, you, Antonella, full time. But we have a long involvement by many other people since 10 years, I guess.
Ulisse, which is
Yes, Ulisse, just to mention one, who made a very important work on the photometric choices of the filters. And anyway, all the community is involved, of course, in it. We have a great expectation from Gaia. We were a bit worried at some point when, just after the lunch, but
difficult times.
Yes, a difficult moment, but it seems that everything has been overcome successfully. So really, today is a great day, and I thank all these people who are worked for making this possible. So I ask you to clap at them, because I think they've done a great job.
Ok, mentre aspettiamo il video, c'è qualcuno che vuole chiedere qualcosa? Purtroppo, allora, ESA ha preparato un sacco di materiale per la data release, per la press release, che è sotto embargo per un'ora, video e quant'altro, che non potranno essere mandati perché in streaming non si vede niente. Quindi c'è un sacco di lavoro anche della visualization team, che però per ora. Dopo, quando sarà finita la press release, li trovate tutti sulle pagine dell'ESA, tutti i link possibili sono direttamente disponibili sulle pagine dell'ESA. Avete il link a qualunque cosa di performance, movie, immagini, quello che vi interessa. In realtà c'è già stata una data release 0 di una sola posizione di una stella 2 mesi fa per un trasto di Plutone, per verificare l'atmosfera di Plutone. Però insomma era una stella, non hanno fatto grande pubblicità.
i vari database come CDS, eccetera, aggiorneranno la loro posizione degli oggetti su Gaia, cioè ci sarà il database di Gaia.
Il database di Gaia
quando
c'è.
incroci con i vari database saranno già operativi?
Allora, c'è un cross-match già fatto con i cataloghi, nel senso che all'interno del database si cerca una stella come di SDSS, ti dice che stella è in Gaia. Però non aggiorneranno tutti gli altri cataloghi per tenere conto di Gaia, però i cross-match ci sono. Se tu vuoi cercare tutte le stelle dell'SDSS che hanno un certo tipo di ID, puoi fare tranquillamente, ti dicono le sorgenti Gaia che ci sono.
Dentro al database di Gaia.
Dentro al database di Gaia, e tutti i mirror sono tutti uguali. Tutti i mirror sono esattamente identici, dovrebbero avere la stessa interfaccia, quindi è molto semplice, lo so. Purtroppo non li posso far vedere perché sono in marco fino a 12:30 e lì non funzionano.
Stiamo attendendo che si...
Scusa, io ero al meeting Gaia a Relassa e ho capito, anzi aveva funzionato dopo con l'amico portatile, quindi stavo cercando adesso, ma c'è un problema di connessione. E ho capito che c'è un software per cui sviluppato, non so da chi, comunque dentro ESA, non so se è esatto, chi è, che praticamente appunto riesce su richiesta a fare un cross match tra quello che è pubblico di Gaia e un certo numero di cataloghi.
Sono già implementati dentro, perché altrimenti la prima data release che ha solo la magnitudine è useless, nel senso che senza l'informazione di colore.
Quindi
questo è dentro dalle 12:30 in poi, sì. Certo bisogna capire come funziona, ma sì.
Rispetto a questo tu accennavi al fatto che la precisione astrometrica superiore potrebbe cioè far sì che se la gente prova a farlo da sé magari
Sì, trovi degli errori buffi, a meno che non metti qualche filtro in magnitudine, ma siccome la banda passante di Gaia non è ancora nota, c'è solo una nominale, potresti avere degli errori nella magnitudine finale. Ci sono pubblicate delle pre-launch version delle trasformazioni tra le magnitudini Gaia e tantissimi sistemi fotometrici. Nomina, mentre la magnitudine di Gaia si è visto essere diversa, è diversa. E questo verrà fatto più avanti, per ora però non è ancora disponibile la trasformazione. Quindi se metti l'informazione in magnitudine come vincolo per questo cross match puoi fare degli errori. Solo posizionale, la precisione di Gaia è così, quella degli altri cataloghi è così. Quindi ti trovi in un brodo. Ci stanno quelli di SDC, la Paola Marese che ha lavorato qui, ha fatto la tesi di dottorato qui, è in charge in ASI di fare questa cosa e sono loro il software ufficiale che fa il cross match e sono quelli implementati dentro. Poi ci sono altri software un pochino meno precisi se vuoi, che non sono adatti al singolo catalogo ma sono di general purpose e sono mi sembra dal gruppo di ESA di Madrid, però non sono tagliati per il singolo per il catalogo specifico. Possono introdurre degli errori se le stelle si muovono tanto, se hanno moti propri elevati, se i colori sono strani, se la precisione in alcune zone gli errori sulle coordinate sono correlati, tu rischi di non trovare la stella che vuoi. Appena saranno fuori le trasformazioni in magnitudine, allora avrai dei vincoli, però per il momento è meglio fidarsi di quello che c'è dentro, che è stato verificato sui singoli cataloghi.
Aspetta, e cerchiamo di parlare sul microfono, se no in streaming non sentono.
Grazie Rosanna, facciamo un salto sugli oggetti extragalattici.
Sì.
Quanti ne sono stati identificati, come verranno catalogati?
Nella data release 1 non è possibile fare classificazioni, perché solo con la magnitudine non è possibile. Certo, se osservata da SDSS tu hai direttamente l'informazione, perché hai il cross match con SDSS, per dire. Dalla data release 2 hai anche i colori, allora con i colori, un colore e la fotometria riesce a fare una classificazione, verrà pubblicata dalla DR2 una classificazione preliminare basata sui colori. Questa è l'idea almeno di farlo. La parametrizzazione delle sorgenti viene fatta dalla data release 3, quando gli spettri saranno ridotti. Perché io ho parlato di fotometria e ho parlato di astrometria, non ho parlato né di spettrofotometria a bassa risoluzione e neanche di velocità radiali. Quelle ci vuole tanto più tempo per riuscire a ridurli, perché il segnale del rumore al momento è basso. In più le procedure di calibrazione sono un incubo, perché immagina il livello di bias che cambia ogni secondo, il background che cambia ogni secondo e devi tenere in considerazione per ogni secondo. Se il satellite ha un movimento dovuto agli asteroidi, ti cambia il background e devi essere in grado di gestirla, quindi ci vuole più tempo per questa cosa qui. Quindi dalla data release 3 avrai anche la parametrizzazione delle galassie, star formation, very basic, però saprai quali sono le galassie con una certa probabilità, chiaramente, quali sono le stelle, quali sono i quasar, eccetera, e di quelle avrai il redshift.
Quello che viene identificato è la parte lineare.
Sì, la source detection di Gaia è speciale, nel senso che solo ciò che è puntiforme viene riconosciuto da Gaia come una sorgente degna di nota. Quindi se la galassia è estesa, hopeless. Ci sono dei modi per recuperare le informazioni sulle galassie estese più avanti, di recuperare un'informazione morfologica ricostruendo delle immagini in base alle informazioni, ma questo viene più avanti nella missione. Cioè se hai tante osservazioni di una galassia, perché hai dei clump di formazione stellare, delle regioni di formation intense che vengono riconosciute come separate da Gaia, magari riesci a fare una immagine e a fare una morfologia, però più avanti è solo di alcune. Quello che viene visto sono le galassie con un nucleo e poco altro intorno, altrimenti Gaia le rigetta, proprio non le prende in considerazione.
Quindi mi immagino che anche gli errori che ci sono enormi, nel senso che è molto più facile per una point source essere identificata anche con una barra d'errore che mi dicevi prima tra il nuovo catalogo ed il vecchio catalogo, figuriamoci per le galassie che magari hanno sorgenti un po' più smooth nella parte centrale.
Allora,
cioè già le
teoria,
determinazioni
le simulazioni che abbiamo fatto ti permettono di dire che siamo in grado di parametrizzare con una relativa bontà, non ti so dare i numeri in questo momento, tutte le sorgenti che vengono. Certo che il numero di galassie che viene preso rispetto a tutta la popolazione della galassia, questo non te lo so dire, ci sono delle simulazioni fatte, ma sono circa 500.000 di galassie che verranno viste e di cui avremo la parametrizzazione.
USO eccetera.
Aspetta che dovrebbe cominciare.
Lo streaming da ESA non è ancora iniziato.
Io riprovo.
Fai un reload, anche su Media INAF hanno messo lo streaming, ma io sto facendo dei reload ma non funzionano. Se qualcun altro nel frattempo ha una domanda o qualcosa.
Dal vivo ora, però io non vedo niente. Lo streaming è avviato. Scusatemi, cerchiamo di controllare.
Chiedo a qualcuno se lo stanno vedendo, ma dubito.
Prova a accedere col mio per vedere se... ma io non ho fatto collegamenti né niente.
Loro dicono di essere in rete perché né su Media INAF né su ESA,
No.
Su YouTube c'è...
Andiamo bene. Ok.
No, anche Simone mi conferma che niente da fare, anche dai computer, quindi non è la rete qui o... Il programma prevedeva le 11:30 l'inizio. E niente, attendiamo. Se qualcuno ha domande mi chieda sempre il microfono. Aspetta, microfono. Per favore parlate sul microfono perché sennò non si sente.
Senti, io non trovo ancora sulla pagina lì dell'ESA, volevo delle notizie sulle parallassi a moti propri.
Largo, fino alle 12:30.
Fino alle 12:30 che sono adesso però, 11:30.
12:30, CEST, 12:30.
Ma abbiamo l'ora legale, quindi?
No, 12:30, fra un'ora.
12:30, ah. E quindi questo verrà reso noto tra poco?
Sì, che cosa ti interessava, che magari lo so.
E mi interessano appunto parallassi a moti propri, con che precisione fino a che magnitudine, perché devo ricalibrare tante cose che ho fatto.
Sono delle cose già note.
Quelle che ho trovato in rete però non lo so, può darsi
Sei
che tu
arrivata
abbia...
tardi, quindi non hai visto la mia slide con riassunto. No, adesso sto scherzando. Allora, per 2 set astrometrici ci sono, 2 set di dati. Uno più limitato, 2 milioni di oggetti, quelli osservati da Tycho, per i quali hai moti propri parallassi e posizioni, brillanti fino alla 11.5.
Sì, vabbè, non mi interessano ovviamente.
Le parallassi e moti propri solo per questi. Gli altri devi aspettare l'anno prossimo.
Quindi dobbiamo aspettare l'anno prossimo, quindi non c'è ancora nessuna risposta.
1 miliardo di stelle fino alla G20 non c'è l'informazione astrometrica, c'è troppo poco tempo. Gaia ci mette tempo.
Certo.
Siamo riusciti a fare una patch, siamo riusciti a far uscire questi, perché c'erano le informazioni di Parcus e di Tycho, ma senza questa informazione.
Quindi è proprio come c'è scritto lì, cioè perché lì dà fino a 11,5 appunto per la moti proprio precisione, però quindi non c'è nient'altro.
Tycho 2.
Quindi Polina può lasciare la tesi così com'è.
Non so cosa che magnitudine ne servono, ma
15, 18.
No. Niente da fare. Vedi, adesso sono online, per esempio le performance qui, se qualcuno è interessato, sono online sulla pagina ufficiale di Gaia. Con le correlazioni in questi diagrammi virtualmente inutili, ma ci sono le tabelle nei paper. Niente. Aspetta. La prossima è a fine dell'anno prossimo, è prevista per la fine del 2017. La data release 2, adesso non so bene dirti che cosa ci sarà perché dipende dalla qualità della data reduction, ma le informazioni di colori e l'aggiornamento di tutto questo senza usare i prior di Tycho, quindi senza i sistematici che abbiamo adesso dovuti alla precisione di Tycho. Vabbè, non so cosa dirvi.
Neanch'io, adesso
provo a mandare un mail a vedere se qualcuno mi risponde.
Prova a contattare qualcuno.
Sono multitasking, se qualcuno risponde a domande sono qui. Ecco, vedete il mio mail, ma
guarda che lo stanno vedendo anche in streaming.
Lo so, i miei amanti li vedrete, ma
io avevo mandato un'immagine, Martina, avevo mandato un'immagine che hanno buttato fuori dalla press release di ESA, molto bella, che magari se si riusciva a metterla, te l'ho mandata su Aula Rosino, se si riusciva a metterla sul PC, intanto era un'infografica bella sui dati che magari Rosanna ci commentava, era in italiano. Ah, ok.
L'hai mandata a me?
No, a Martina. Che
ogni volta che c'è uno streaming qualcuno non ha messo i permessi.
Non so dove prenderla però adesso sta immagine. Allora. Chi mi sta chiamando? Chi è che mi chiama?
Io.
Martina, qui sopra.
Ah, scusa.
Vuoi attaccare il tuo PC?
Se
vuoi attaccare il tuo PC.
No, non ho il adattatore con me, è un Mac. Comunque niente, non è disponibile.
Ok, spero che questo non sia interpretato come una cattiva qualità dei dati.
Eccola
Gaia,
qua.
sarà meglio.
Non so Rosanna, se ti piace questa, è bella questa immagine,
Sì.
se vuoi
Io ho un po'
commentarla
di
un
numeri.
attimo, a me servirebbe per la parte divulgativa.
Ok. Sì, non è che ci sia molto qui, no. Aspetta, vediamo se ho qualcosa qui. Ecco, se a qualcuno interessa, queste sono le precisioni. Scusatemi, controllo se... Possibile Oddio, aspetta che vediamo se lo fanno. Sai che non me lo ricordo della data release 2? Non me lo ricordo. Adesso vado a vedere perché il fatto è che i dati di Gaia sono attesi per il 2020. I dati di Gaia arrivano nel 2020. Tutto quello che viene prima è un bonus di quello che riusciamo a risolvere per ogni stella sono milioni di equazioni astrometriche, deve essere tutta autoconsistente. Finché non hai abbastanza dati, o è risolvibile o non è risolvibile. E con solo 2 anni di dati non è risolvibile la... non me lo ricordo. Nel 2020 è questo qui, fino alla 20.7. 20.7, la G20.7. Sì, ma devi avere pazienza. Anch'io devo avere pazienza.
Fino alla 20.7 che cosa?
G. Avrai tutto quello che c'è scritto. Fotometria, astrometria, ma non le velocità radiali, chiaramente, non fino alla 20.7. Parallassi, astrometria, posizione, parallassi non più proprio, fino alla 20.7. Al catalogo finale però.
E il prossimo anno parallassi fino a dove siete?
Non me lo ricordo, devo andare a guardarlo, però non ho il materiale qui.
Lo vuoi guardare?
No, perché non è il mio...
Speravo sia rimasto più verso la 15.
Te lo mando dopo perché non ho il mio computer qui, non saprei dove andare a cercarlo. Aspetta che vediamo qua, aspetta un attimo. Ma non è che ce li possiamo non è che ce li teniamo noi, perché la cosa buffa di Gaia è che noi non vediamo i dati prima di voi. Cioè io non vedo i dati di Gaia prima di te. Quando sono pronti vengono release alla comunità e allora noi possiamo guardare i dati, se non per la validation, ma non ci possiamo fare scienza sopra finché non sono pubblici. È un po' crazy, ma è così. Dimmi tutto.
Una se facciamo.
Sì.
Cioè, non ho capito come mai. Capisco gli anni connessi con l'astrometria, moti propri e parallassi.
Sì.
Non capisco gli anni come si correlano con la magnitudine limite, perché tu parlavi di soluzioni astrometriche.
Sì, ma infatti secondo me arriva fino alla fine per la soluzione astrometrica, quando li pubblichiamo è la 20.7, ma non voglio dire una sciocchezza. Non mi ricordo cosa c'è nella data release 2, vado a vederlo perché non me lo ricordo sinceramente. No, non si correla, infatti me lo dicevi con sicurezza ma non c'è. Eccolo qua. Data release. Second data release. La soluzione astrometrica per il 90% del cielo, quindi è fino alla Sto rispondendo, Marina. fino alla G20 nella second data release per tutte le stelle c'è la soluzione astrometrica. Se c'è, sì. 5 parameter, non c'è la velocità radiale, quella no. Ok? La BP, la magnitudine G, BP ed RP, le velocità radiali medie per le stelle che si comportano molto bene, non variabili, eccetera, eccetera, per circa il 90% del cielo. Pending validation, pending l'analisi dei dati. Questo è quello che noi ci siamo previsti di fare. Purtroppo avevamo anche uno streaming, ma non c'è lo streaming.
Mi confermano anche da Roma, anche da Medica,
anche da loro?
Cioè non vedono, è tutto bloccato. Non hai
Antonella non
WhatsApp per Antonella?
Non è online?
Strano che ESA sia così.
Prova a mandarle un WhatsApp, hai ragione, ma non hanno messo i permessi, hanno sbagliato i permessi del video. Guarda, cioè, non ha reso disponibile il video, non è che mi viene in mente niente altro.
I video che dovrebbero rilasciare alle 12:30, scusami, non so se l'hai già detto, è che ero presa da cosa
Sì.
contengono, ce lo puoi dire a parole
vedo
dopo?
se-
Ok, sì.
L'hanno detto? Yes! Quindi siete bloccati qui ancora un gruppo. Vabbè, se...
What's in the tweet? Yes, we have stopped the Gaia Database number 1 press event until the streaming issues are resolved.
Scusate, no, un attimo.
Hanno un problema nello streaming e hanno bloccato la presentazione finché non...
Okay, there is a Twitter. We have stopped the Gaia data release number 1 press event until the streaming issues are resolved. Our team is working on it, stay tuned.
Sì, stay tuned. Sono così? Veramente, veramente. Riescono a fare dei video meravigliosi e si bloccano con lo streaming. Non è bello da dire, ma è tristezza. Peraltro non vi posso far vedere il Gaia Archive perché è sotto embargo, non vi posso far vedere i video perché è tutto sotto embargo. Non posso far vedere niente.
Se andiamo sul Facebook di Media INAF ci sono le dirette di Elisa Nichelli che sta magari facendo qualcosa, provo io.
Sì, dai.
Tieni, se qualcuno parla, prova a dargli un...
Dimmi, grazie.
Ricordi la collaborazione, ESA, c'è la NASA dietro?
No, la NASA non c'è, è tutto europeo. Tutto europeo. Sono 400 scientist in Europa. L'Italia mi sembra che sia la seconda come numero di collaboratori dopo la Francia. E c'è un bel impegno finanziario anche dell'Italia dentro, ovviamente, oltre al numero di persone. Siamo ben messi nei vari centri di data reduction, abbiamo delle posizioni di rilievo. Antonella è la deputy chair di tutto il DIPAC. In tutta Europa, sì, ci sono tutti i paesi coinvolti, la Germania, l'Inghilterra, Spagna, Francia, tantissimi.
Astronomico di Bologna e non solo, scopriremo, che ha un ruolo fondamentale all'interno della missione Gaia. Ce lo facciamo raccontare dai diretti interessati. Raccontateci un po' chi siete innanzitutto e che cosa fate.
Carla Cacciari, CU5.
Io sono Carla Cacciari e lui è Giuseppe Altavilla. Siamo in rappresentanza, c'è anche Angela che però è scappata dentro, ma insomma, lei è...
Sono Tatiana Muraveva, io sono russa però lavoro adesso in Italia.
Cosa facciamo? Lo stoppiamo questo? Lo mettiamo in piccolo?
Noi a Bologna avevamo l'incarico di fornire la calibrazione
Ovviamente uno dei task fondamentali è calibrare questa fotometria, e gli spettri più che altro, quindi c'è un grosso lavoro da parte dell'osservatorio di Bologna per osservare le standard, ridurre le standard fotometriche necessarie per la calibrazione di Gaia. Quei piccoli jump che vedevate nella distribuzione degli errori sono dovute alla ancora mancanza di dati sufficienti per calibrare alcuni range di magnitudini. Non ci sono abbastanza standard osservati in Gaia con un certo tipo di magnitudine perché nei vari passaggi di riduzione fotometriche non erano state osservate, per ridurre questi piccoli jump negli errori. Ci sono a diverse magnitudini si attivano dei gate per evitare delle saturazioni e bisogna calibrare bene il passaggio da un gate all'altro perché le condizioni fotometriche sono diverse. Questi passaggi li vedete dei piccoli errori, aumenti dell'errore fotometrico, perché ovviamente di tutto si tiene conto nell'errore. C'è stata un'intensa opera di validazione del catalogo, sono 4 mesi che stiamo lavorando per controllare tutto con tutto e siamo certi che questi siano degli errori accuratezze, non precisioni. Ci sono dei sistematici di cui tener conto, che sono tutti documentati, però siamo già come prima data release per quanto riguarda la fotometria a un ottimo livello di precisione e di accuratezza.
La fotometria deriva dalla spettrofotometria, se non sbaglio.
La fotometria in banda G no, è luce bianca che entra nello strumento astrometrico che non è disperso. La fotometria in banda GBP e GRP deriva dalla spettrofotometria come integrata, ma la riduzione della fotometria integrata e dello spettro va in 2 binari diversi, per cui dalla data release prossima avremo la fotometria integrata, calibrata come se fosse fotometria. Per la spettrofotometria la procedura è più complessa e si aspetta un'altra data release. Sono calibrazioni complesse. Vediamo. Quando vi stufate vi ringrazio, capisco che sia difficile stare qui sul niente.
Puoi dire che cosa è stato fatto qua? Perché su quella piantina lì c'è scritto evoluzione stellare Padova, evoluzione stellare.
Noi come Padova entriamo in gioco molto dopo, perché entriamo in gioco per quando riguarda la classificazione delle stelle e la parametrizzazione delle stelle. Quindi dalla data release 3. Lavoriamo dall'anno come specifico per la data reduction e per misure che entrino nel catalogo, entriamo in gioco l'anno prossimo quando gli spettri sono calibrati. Senza gli spettri noi non entriamo in gioco. Certo, stiamo già lavorando per avere gli algoritmi pronti perché altrimenti non si può fare. Il grave Yes!
Can we get higher even precision than Gaia in a specific field of view, a smaller field of view, so that we can look into
Martina, il volume non si sente.
Accurate measurement, astrometric measurement for cases like, for example, the discovery to find out Earth-like planets. How can we characterize them with this kind of measurement? All these things we are thinking, but they are based on what we do with Gaia nowadays. The results of Gaia provided to the scientists as new questions, new ideas to develop, and this we will hear today. This I'm very glad to see that we are getting data that are really fantastic and that they show we have a great mission, but we have even greater future. Thank you very much.
Thank you very much, Alvaro, the Director of Science here at the European Space Agency. And before I was talking about the coin, I'm not taking it out again, don't worry, but it's about precision. And when we started to operate Gaia, we already knew we need to be really, really good in this. And Fred Janssen, the mission manager, is now going to explain to us what it means to operate Gaia, that you really get a very stable performance over years with billions of billions of billions of billions of measurements, which we need, again, to come up with the galaxy map, which will allow us to look into the past, its current state, and into the future. Please welcome with me Fred Jansen, the mission manager of Gaia.
I'd like to give you a short summary of what it means, why we need to operate at the limit of precision, and how you operate at the limit of precision. What are the challenges? How do we actually measure a star's distance? What do you need to do? Let's start with that. The mechanism is already known for a long time. You use the Sun-Earth distance as a baseline. The Earth moves around the Sun, and that means for star at a finite distance, if you see them against the background stars, they actually describe a small circle on the sky because of the apparent movement, because we move in space around the Sun. There is a second effect, however. Stars in space don't just sit there silently in one position. They really move. And they move in 3 dimensions. There's the true velocity of the star, and we see that in 2 ways. We see the projection on the sky of the movement the star makes, but there is the 3rd dimension away from us, which is the velocity. Now, if you combine these effects all together, this is the path on the sky that a star describes over 5 years. Now, this is a very small piece on the sky where we have to do this track. We measure a number of times to be able to disentangle the effect of the distance and the motion through space. And this is what Gaia is really good at. The challenges of Gaia: we need to scan the whole sky with basically something optically is equal to the Hubble Space Telescope. Otherwise, we cannot do the Gaia science. We need to observe 1 billion stars. To do that, we need to go down to what astronomers go magnitude 20. But in real life, this is 500,000 times fainter than what you can observe with the naked eye. We need to observe the whole sky some 70 times during the nominal 5-year mission. And this is to get enough points along the curve on the sky that I showed before to disentangle the effects of movement and distance. We need to determine these positions down to 10 micro-arcseconds, which Marcus already amply explained is the size of a coin on the moon. In order to do the mapping that Gaia needs to do, you actually need 2 telescopes, and I'll explain that in a bit more detail in a minute. But these 2 telescopes actually image on 1 big camera, and you can't afford to fly 2 cameras, and it's not necessary, and Gaia needs to enable this. We need to determine the velocity through space of a subset, not all of the billion, but a good subset of these observed stars. Now, how actually do you meet these challenges? We need a large aperture, high-quality optics of Hubble Space Telescope quality with a 1 billion pixel focal plane camera. That's 106 CCDs. This gives you an impression of what one of the 2 Gaia primary mirrors actually looks like. And you can see that it's impressive size, and it's real excellent quality mirrors. We need to observe simultaneously with 2 telescopes separated by an extremely stable angle. We measure that angle with a device internally, an interferometer. But why do you need to observe with 2 beams? Well, intuitively, you can imagine if you have 1 telescope looking to the sky, you will never be more precise than your knowledge of where you point, of actually your star tracker in the normal satellite telling you this is where you are. Now, if you have 2 fields of view which scan the sky and successively see the same stars, you can imagine that this gives you an impression of what these 2 fields of view of Gaia look like internally to Gaia when we remove the outside. You see here in gray the Gaia torus, and on top of it mounted the 2 primary mirrors. that's not just it. The light goes through the system in an incredibly complicated way, and at the bottom right, you see the backside of where the camera with 106 CCDs is mounted. Now, this system needs to be incredibly precise to be able to do this, and that's why all of these objects are attached to one silicon carbide torus, making the whole thing immovable and allowing us to do the precise measurements. We need a spinning spacecraft. We need to see the full sky. You don't do that by patchwise looking at the next spot every time, but you do that by continuously spinning and looking at the sky in a moving way. This is how this is done, and this is an artist's impression of the viewing directions Gaia sees, and then continuously it moves around. That allows you to see the same stars twice with these angles separating the two beams, and then the satellite slowly precesses and moves over the whole sky. We need extremely precise timing, because Gaia scans the sky, but in order to get enough light, we need to read out the focal plane camera, the CCDs there, in exactly the same rate that Gaia scans the sky, because otherwise the point sources, the stars, smear out and are not points anymore. We also need to know to unprecedented accuracy where the spacecraft is on the sky. And actually, we need to know better than 100 meters. And this accuracy is largely related to solar system objects, which, it may sound strange, are so near to Gaia that if you don't know its position better than 100 meters, you can't really determine how they move through the solar system. To do this, we use special measurements, which ESA does with other spacecraft like Rosetta as well. This is called delta DOR, delta differential ranging. This is a very complicated technique, but we need 2 ground stations to do that. And ground stations are a sparse resource, and they also cost a lot of money, relatively. So we also use ground-based optical telescopes to actually see Gaia on the sky and tell us where it is to the accuracy that we need. We've recently seen the first batch of those results, which are not yet included in the whole data release now, but we know this technique works, and we will use that to precise Gaia's position on the sky to allow us to do the solar system object science in the future. We have a very high data rate. You can imagine that if you see 1 billion stars 70 times, and Alvaro already told you that to date we have 500 billion astrometric measurements, we have a large data volume. This needs to go to the ground. Now, that A is a pretty impressive bit rate. Let's put it this way. 10 years ago, I would be very happy to have that type of data rate at home on my internet connection. But we need to get it from Gaia. And not only that, you need to get it from a satellite which is continuously rotating and moving along the sky. You can't just have your parabolic dish. You need a special antenna to actually allow the automatic steering of the beam to Earth in an electronic way. Now, these are the challenges of Gaia, and this is how we met them. Now, what we have today is the first of a number of data releases, and I wanted to give you a feeling for the complexity that we're going to add over time. I won't bore you with all the details in this table, but you will see that there are 3 more data releases like this planned in the nominal mission, and then there is one at the very end. We will see more photometry coming in. We will see spectrometry, the accurate measurements of the velocities of stars. We will get the characterization of stars in terms of temperature, things related to composition, etc. We will get the individual measurements will at the end of the mission be released. And that's, of course, where things get really complicated, but also where a lot of astronomy can be harvested from the Gaia data. So I'm extremely happy with the data release today, but I'm even looking forward to what we will see in the future. Thank you.
Thank you very much, Fred. Ladies and gentlemen, Fred Jansen, walking over the stage, the mission manager of Gaia. And I can say hello again, meaning we are online again, so we are streaming again, and I take this opportunity to apologize because if we're missing the first part, we will put it online as soon as the live stream is over and on demand so that you can see that as well. And having said that, now we are moving from precision to the science, but also to the huge heritage ESA and Europe has in astrometry, because we have been launching way back Hipparcos, and a lot of astrometry and astronomy is based on the data from that satellite, and now we are getting Gaia, so we are pretty happy. And the way from Hipparcos to Gaia and this outstanding map next year will be explained by Timo Prusti. He is the mission scientist at ESA on the Gaia mission.
Thank you. I will move now from the technical challenges into the scientific aspects what Gaia is going to address. So I will detail a little bit what the precise map of our galaxy means, how do we do it and why do we do it. So the scientific key requirement for the mission is to understand our Milky Way galaxy better. Milky Way galaxy is a little bit abstract concept. If you have a dark night, clear sky, and you go and look out, you see stars, but you actually don't really see that we are part of a system which is flattened. We are quite far away from the center of our galaxy. The concept of spiral arms is totally invisible to us, yet that's how our galaxy is all about. In a way, Milky Way is an easy target. Wherever you look at Milky Way. At the same time, it's extremely difficult because in order to understand it completely, you have to look to all directions. And there are various components in the Milky Way galaxy which all interact and play a game with each other. And we have to map all of them to have a complete picture how our Milky Way is operating. So we do want to see what is happening in our solar neighborhood around us. We do want to see what is happening in the galactic center, the so-called bulge. How are the stars moving there? We have globular clusters, stellar clusters around our galaxy. We want to look how the stars are moving inside those ones. And we have the bulk of the stars which are in a disk-like structure. How are the spiral arms? What kind of stars do we have in the various distances from us? What are the chemical components of it? How do they move? That's all what we want to achieve with Gaia. But we are not going to be lifted off from the galactic plane and take a picture. We have to take pictures from Gaia. Actually, Gaia is not making any pictures from the sky. We can do it, and we have done it for this globular cluster just to show the richness of what Gaia is seeing. Gaia sees this kind of sky, but how Gaia is operating, it does not take this picture. It is looking at the moment it is observing, and every time it sees a star, it identifies it and takes the measurement of that specific point. Anything what is here black will not be transmitted to ground. Anything where you see light will be transmitted. For most of the sky, most parts are actually black. So that's why it is the most efficient way to get the key information from Gaia down. We do all these points. We do the astrometry, position. We do the photometry to get the colors of the stars and to get handle on the physical properties. For the brightest ones, we do spectra. And we do a survey containing several million stars where we can really look at the details how the stars are looking. We get understanding of the composition, what kind of material was around when this star was born. That will give us a handle how stars are born, what time, and which chemical composition. But let me move a little bit outside from galaxy, just a sidestep. As already mentioned, Gaia is also observing other sources because it is a very democratic mission. Anything what looks point-like is caught up and observed. So we get million galaxies. We get 500,000 quasars. Extremely important because finally we can align reference frames from radio wavelengths and optical wavelengths. We will know in both wavelengths what we are looking the same thing on the sky. In the future, all satellites which have star trackers, they have a Gaia catalog in them. It is the Gaia which tells them where they are pointing. When we go to solar system targets, we are observing 250,000 asteroids, get their composition, very precise orbits of them. And sometimes we get something else, like in this example, just raw data, Pluto and its moon Charon, we see as two separate sources. And just by raw data, we can already see they are revolving around each other. And one of the products from Gaia will be all these precise orbits telling how the solar system is functioning. Let's go back to galaxy and looking at what the horizons are, what we are seeing. Hipparcos was already mentioned as an important ESA mission earlier. It made a revolution in astronomy. The distances really changed how we think about stellar evolution, and it's a building block what was needed to get a better understanding of stars. In a galactic scale, the blue ring here is the reach of Hipparcos, where we get the good distances to stars. So you can immediately see that if you say that I want to understand how our Milky Way galaxy is, you need to go a little bit further. And what we are doing with Gaia, we are observing, we continue observing, and we are stretching our reach to get the same accuracy what Hipparcos provided in the solar neighborhood. We are moving into galactic scale. And we are going to see the spiral arms, and we are going to look what happens around the galactic center. Now, this is all promises for the longer term, and I just want to round up, saying a few words of the release today. It is important release. It is important for us who have been working in the mission. It's a milestone. We can now provide to the community the data for use. So it's like an endpoint of phase 1 in our project. But it is also a very important point to us as a starting point, because a lot of us are motivated to work on the data. So we are looking 12:30 eagerly to use the data, to enjoy the science, and my advice to the astronomical community is, please enjoy with us. Thank you.
Thank you very much. Timo Prusti, ladies and gentlemen, the mission scientist on the Gaia mission at ESA. And now we are coming to, how shall I put this, a very nice European story, because all the data processing analysis is done in a huge group of European scientists located all over Europe. And for you here in Spain, we have some of our colleagues that come from the University of Barcelona. Also a very important part in this effort to make sense out of the Gaia data. So if you want to talk in Spanish to your Spanish colleagues, then feel free afterwards. Now I'm going to ask Anthony Brown from the University of Leiden on stage, and he is the chair of the DPAC consortium, and he can give us a kind of a sneak preview into what Gaia really sees. Thank you, Anthony.
Thanks, Marcus. Yeah, so I will provide you with a first glimpse of what is contained in this Gaia data release. And I'm standing here really on behalf of a very large consortium, as Marcus just mentioned. This is the Gaia Data Processing and Analysis Consortium. And this consists of about 450 scientists and engineers, software engineers, located throughout Europe, who have worked very hard over the past 10 years, some of us maybe even over the past 15 or 20 years, to realize this first data release that we are presenting today. They are located in 160 institutes spread all over Europe, in 24 countries, and also ESA makes a very important contribution, and many of the ESA people who have been working also providing excellent support to the mission are here today, so I'm very happy to see them. And the data processing that we do for Gaia, so we take all the raw telemetry that comes from the mission, all these zeros and ones that you see coming in from the sky, and we turn them through our 6 data processing centers into data products that the scientists can actually interpret, that astronomers can use. And this is what everyone is excited about. This is what I'm personally also very excited about. And I'm looking at my watch. It's only 20 minutes more for the astronomers out there, and then they can start looking at the data. So, what's in the release? So first of all, we have a billion-star atlas, as I call it. So here you see a schematic representation of a sky atlas, and you can recognize a famous asterism, the Big Dipper, as it's called in English, and it's part of the Ursa Major constellation. And this is, of course, easily seen from the northern hemisphere. And we will have such a map with Gaia for 1 billion stars, out to magnitude 20, as was mentioned before, so for stars that are about 500,000 times fainter than you can see with the naked eye. So that's the first component, these billion stars, and we have pinpointed them very accurately on the sky. The second component is what I call a 3D motion picture of the brightest 2 million stars in our neighborhood. So these are the brightest stars that we have in the catalog, and for these stars we were able to measure the distance using this parallax technique that Fred explained before. So the fact that the Earth moves around the sun makes the star apparently move in a circle on the sky, and that we can use to infer the distance. But apart from this distance, we can also measure the motions of the stars across the sky. So stars are not standing still over time, they move across the sky, and that's caused by the fact that they are moving through space. And I take here again the example of the Big Dipper, and I've indicated with red arrows the motions that these stars have across the sky. And you can see that these arrows are all directed more or less in the same, in the same direction. And that's because these particular stars in this constellation actually are related to each other. And we know that because they're all moving together in the same way. And this is a very important ingredient for us in the disentangling of the history of the Milky Way, and as we'll hear later on also about understanding star clusters. Now then, finally, we have a third component, and these are so-called twinkling stars. These are stars that vary up and down in brightness, and you see here a particular example of that. So you see how the star changes its brightness as a function of time. And these stars are extremely important in constructing the cosmological distance scale. So with Gaia, we are able to measure distances very near the sun to very high accuracy, and throughout our own galaxy. But if we want to go beyond, if we want to go to our neighboring galaxies and the whole universe, then these particular stars play an extremely important role. Okay, so now let's have a look at the Gaia map, so the billion star map. And it would be good if the lights could be switched off so you can really appreciate this, this image. And I'll just let you look at it for a little while to appreciate this first image from the Gaia sky. And I think this is already, no, down. And I think this particular image is already really stunning. So what you're seeing here is an image of the entire night sky. And what you see is in the light regions, the white regions, there you have high concentrations of stars, and in the black patches, that's where you have very few stars. And you see a big bright band running across the middle of the image. That's the Milky Way, which you can see especially well from the southern hemisphere, but also here, in particular in Spain, where nights can still be very dark, you can see this Milky Way. And in the Milky Way itself, you can see lots of dark patches, and these are actually clouds of gas and dust that sit between us and the stars behind them, and they're basically blocking out the starlight, and that's why they appear to be black against the background of all the bright stars. You see another prominent feature, which is the two small galaxies in the lower right of the image. These are the large and small Magellanic Clouds. These are two neighboring galaxies, dwarf galaxies, that are orbiting our own galaxy, and they can be very nicely seen also with the naked eye from the southern sky, not from here. Now, another very important feature that you see is if you follow the image from the, all the way from the lower left, and you go across the middle, and you go up to the upper right, you can see that there's lots of striping patterns and areas where there appear to be more stars in a kind of artificial way. And these are not astronomical features. These are caused by the way that Gaia scans the sky. And it shows that this map is really still a work in progress. And so we expect these features to disappear with future data releases, but right now, in this image, you will see this characteristic, and this also makes it really a Gaia image of the Milky Way. Now, what is furthermore special about this map is it contains 1 billion, more than 1 billion stars, so it's the largest ever map made from a single survey, and it's also the most accurate map ever made. It has a positional accuracy for each individual star of the order of 10 milliarc seconds already at this stage, and it will get much better as we go along with the mission. And the last thing I want to mention about this map, this also came to the front in Fred's talk, is that the spatial resolution of this map is comparable to that of the Hubble Space Telescope. So you have to imagine taking pictures with Hubble Space Telescope, but then of the full sky. That's effectively what you're seeing here. Now let's, to further appreciate the richness of this map, focus in a bit on a couple of nice regions. So the first one is near the direction towards the galactic center. And these are dark clouds called the Rho Ophiuchus clouds. They are in the constellation Ophiuchus. And they are actually clouds that are fairly near to the sun, a couple of hundred light years away. And in these clouds, currently, stars are being born. New stars are being formed. And what is special here is that we can, because we have so many measurements of stars in the neighborhood of the clouds, and they're so accurately positioned, we can actually really outline in very fine detail the shapes of these clouds. And what's even better, in the future, for the stars that you see here in this image, we will get distances from Gaia. They're too faint now to get distances to all of them, but in the future we will have that. And then we can actually tell where the cloud is in 3 dimensions. And this is a unique thing that can be done with Gaia. So then we go to the next region, which is a personal favorite of mine. It's centered on the constellation of Orion, which is easy to spot also from the northern sky. And what is special here is that in the Orion constellation there are dark clouds, which you normally don't see. And these dark clouds, again, harbor birthplaces of stars. And in most optical images of the sky, these things are not recognizable. But because Gaia has observed so many stars, you can actually see the faint outlines of these dark clouds against the stellar background. Now, next we focus on a region which is empty of Milky Way stars, but it features 2 galaxies outside our own. In the upper right of the diagram, you see the Andromeda Nebula, the Andromeda Galaxy, and in the lower left, you see the Triangulum Galaxy. Both of these are big spiral galaxies like our own Milky Way, but located very far away. And what is special about the way that we see them with Gaia is that we detect individual stars in these galaxies across many hundreds of thousands of light years. And these individual stars outline very nicely, for example, the spiral arm structure. And then lastly, I show a blow-up of the Large Magellanic Cloud. This is really a beautiful little galaxy, dwarf galaxy, orbiting our galaxy. And you can recognize again the richness of structure in the Gaia map. So you see in the middle what we call the bar of the Large Magellanic Cloud, and it's surrounded by what looks like almost a spiral structure. And you see also many bright little dots. And these are actually concentrations of young, bright stars that have formed maybe only a few million years ago and are still shining brightly, and they are almost speckled like jewels across this image. So it's impossible to show all the richness of the map, so I definitely encourage you to download the big high-resolution versions that we are making available today and explore them for yourself. We are also making available an annotated version so that if you don't know the sky, you know what you're actually looking at, and if you do know the sky, you can easily look up what you want to see. So go out and enjoy that. Okay, now we go to a different topic, and this is really a demonstration of the fact that the distances that we measured with Gaia for the 2 million bright stars are reliable, are accurate, are scientifically of very high value. This is a diagram which we call the Hertzsprung-Russell diagram, and we use this to study the physics of stars. And in this diagram, we plot the brightness of the star, which is on the vertical axis, and this is the intrinsic brightness of the star, which we know because we have measured the distance to the stars. And we also show the color of the star. So we have blue stars in the lower left of the diagram, hand of the diagram, and on the right-hand side, you have red stars. Now we know from our insights into stellar physics that most of the stars live on the so-called main sequence. That's where they spend most of their lifetime. And this is the big band running from the upper left of the diagram all the way down to the lower right. Now as stars grow older, they evolve, they become larger, they turn into so-called giant stars. And these are located in the upper right-hand part of the diagram. So these are stars that are for 100 to 1,000 times larger than the sun or even bigger. And at the very end of their life, a star like the sun will turn into what we call a white dwarf. This is a tiny star. It's about the size of the Earth, very compact. And you can recognize 3 of those guys all the way down in the lower left-hand side of the diagram. 3 little white dwarfs sitting there, seen by Gaia. So from this, the shape of this diagram, we can tell that the distance measurements that Gaia has done have been very reliable, very precise. Now what is special for the astronomers out there in this diagram is that we have 1 million distance measurements better than 20% in precision. Hipparcos had 60,000 of them, so this is already an enormous jump. And in the future we can expect much more from Gaia. We will have up to 280 million stars that are measured with a precision of 20% in terms of distance, but even 10 million stars are still if we demand an accuracy of 1%. And this is really unprecedented, and it will that's why I can say this will really cause a revolution in stellar physics and also in the calibration of the distance ladder. Okay, then to wrap up, to summarize the first data release that we are presenting today, I think it's a major advance in the mapping of the heavens, which can especially be appreciated in this really stunning image that we now have of the Milky Way based on Gaia measurements. It really represents also a very large increase of highly precise fundamental stellar data. Every area of astronomy ultimately rests on knowing these fundamental stellar data. And all of the results, the data release contents, how it was produced, etc., will be described in scientific papers that will appear in an astronomy and astrophysics special feature, and they are available as of today online. So again, for the colleagues out there, go ahead, download those and read them, but above all, enjoy the data. And I myself, I'm also looking forward to the future. And in the next data releases, as Fred has so nicely shown, we can expect more, we can expect better, and we can expect much richer data sets. Thank you.
Thank you very much, Anthony, the chair of DPAC, for sharing really these amazing images. And looking at the clock, it's still ticking away as if it was a launch, but we still have 7 minutes to go. So stay with us. And what we've been doing, we've been asking 2 scientists who were involved in validating the operations of Gaia to take those data and see whether they really work for them. And the first speaker is Antonella Valinaris. She is from the University of Padova, and she is also associated with INAF. And her specific special topic are clusters. Star clusters, why are they important for the evolution of the galaxy? Please, Antonella.
Thank you, Marcus. So, let's talk a bit about Gaia science. Gaia is an exciting project. It can do a lot of science, but I would like to focus in these few minutes about a very important question. And the question is, how was our Milky Way formed? This is a fundamental question of modern astronomy, and it is around since at least a century. And now we are in a position to say something. And in this topic, the star cluster play a fundamental role. Let's tell the story since the very, very beginning. In the year 6009, an Italian scientist, Galileo Galilei, took a prototype of a telescope that at that time was built and used just for military defense and pointed it in the direction of the Milky Way. This was a useless thing with no reason. But at that time, nobody knew what was inside the Milky Way. It was just fluffy clouds in the middle of the sky. And at his great astonishment, Galileo discovered that the Milky Way is indeed full of stars in all the directions. And the year after, he wrote the book you see there. And this is what we think is the beginning of modern astronomy, because since that moment, the people begin to look at the sky with different eyes. He built, and this is a sort of a revolution that took place at that time. And Galileo built a map that you see there on the right, and is a map of the Orion cluster showing a lot of more stars of what is visible by naked eyes. Now there is a new revolution that is coming, and that is a 6D revolution of Gaia, or better, a multi-dimension revolution of Gaia, because Gaia is going to provide not only the position of the stars in the sky, but also the motion of the stars, and then from further data releases, not in this one, but also the information about how the stars are formed, and a lot of other information about stars. So, let's go back to our topic. How was our galaxy formed? In this context, the cluster play a very important role. What you see there is a star cluster, is an image taken by Gaia at the very beginning of its life to verify that all the instruments were properly working. And you see, because what is a star cluster? Is a concentration of stars that were born together. It's going from 100 to thousands of stars. And it all the key to understand how our galaxy was formed, because all the first clusters, the first objects that were formed are indeed the clusters, and clusters begin to be continues to be formed even now in our galaxy. Is more than that, because what we believe, if we want to understand how the Milky Way was formed, we need to understand how the stars were formed. And we believe that the stars are born indeed in clusters. Here you see a simulation, and what you see is a filament of gas that are collapsing under the effect of gravity. They form this white dot that are stars, and these clumps are collapsing together, are merging together, but in this process, a lot of these little stars are lost. And we believe that those stars that were first formed in cluster and then lost, you see them spreading all over the picture, will populate and form our Milky Way. The point is how this really happened. We don't know the details. We don't know how many stars are lost from the clusters and how many stars stays in the clusters. The clusters lose stars at the beginning of their life, but they lose stars also while moving around the center of our galaxy, and this process is continuous, and we want to know exactly how this is taking place. How many clusters we have in our galaxy? We have a lot of old clusters that were the first formed and are a bit far from us, but then we have the youngest object that are continuously formed in the disk of our galaxy, and let's concentrate on those for the moment. Here you see an artist view of our Milky Way. You see the spiral arm, and now you are familiar with that, the galactic center, and you see a ring, and at the center of the ring there is our sun. You see a lot of white dots, and those white dots are all the known clusters in our galaxy. They are about 2,000, 3,000, more or less, and what you see there is that they are almost all concentrated around our sun. But if we believe that all the stars are born in clusters, we need to find those objects all over the galaxy. And we expect indeed to have about 100,000 objects like that in our galaxy. And this is where Gaia can make a difference and discover new objects, at least in regions where there is not too much gas. So how is Gaia going to help on this? Here, clusters are in general very difficult to be found. Here is an image built using Gaia data in a region where we know there is a cluster. The cluster is Presepe. You cannot see it. But the star clusters have a property. The stars remember that they were built together, and they move around the center of our galaxy all together, at least the ones that are not lost. So if we add on the top of it the movement that Gaia is able to discover, and has already discovered, you see there the little arrows, then you understand immediately that there is an object, because you see a lot of stars moving in one direction and some objects moving in random direction and with a random movement. And this is where Gaia can make the difference, because it will be able to find the movement of the clusters and the movement of the stars inside the clusters. So Gaia is able to give us distances and motions, and this is a field in which already in the first data release we can do much better than Hipparcos. In Hipparcos we had 80 clusters inside 1,600 light years, And in Gaia first data release, we have already 400 clusters, of which we know the distance and the motions, and they are in a volume that is already 9 times larger. And this is just the beginning of the story. We can do really much better. And because here you see a plot where you see the velocity of the stars in left region, taken from Hipparcos data, and we know that in this region there is a cluster, but you cannot see it, you cannot spot it. If you look at the right, you see the Gaia data, and you immediately see that all the stars that move together are clustered. They are in a single position in this yellow, greenish spot, and you clearly see where is the cluster and where are the other stars. So we are, in this way, Gaia is already providing information about these objects. Of course, it can do this just in a region around us, not much far away, but this will come. We wanted to see how good we were doing, so we were doing a lot of checks on the data that are on the archive. And one of the checks we did was to take the 14th cluster that are closer to us and check derive the parallaxes with Gaia and derive the parallaxes with Hipparcos and compare them. And we were using also HST parallaxes, what we had. And what we find is that there is a remarkably good agreement. So we are doing indeed a very good job. Also already in this first data release. There is something else that Gaia can do in this first data release. And this to see the 3D dimensional structure and the internal velocity dispersion of nearby clusters. So how large is a cluster? A cluster is a tiny object. It has a dimension that is going from 10 to 60 light years in a galaxy that is something like 300,000 light years. And Gaia is able to see the three-dimensional structure of a cluster. Now you see this just for the nearest cluster, the Hyades. You see that this cluster is not round. You see that it's elongated, it has a central concentration, and you see something more. You see that the red stars, if you look at the motion of the stars, are on their way to be lost from the cluster and to be spread in the surrounding population of the Milky Way. So we can see the beginning here of the process that goes to the disruption of clusters, forming the stars, the population on the surrounding Milky Way. And to appreciate this, you must know that the tiny motion that Gaia is able to see inside the cluster is really very tiny. It's less than 1 kilometer per second. Imagine that our sun is turning around the center of our galaxy at a speed that is 2,500 kilometers per second. So this tells you how good is the precision of the Gaia data already in the first data release. Of course, we could do this just for the nearest clusters, and the rest will come with the further data releases. We have, in the first data release, we have something more. I told you that we have data for 400 clusters, which we have motions and distances. But we can have also the brightness of many more clusters. Here you see an example, you have already seen it, is the Rho-Fuki star-forming region, and you saw the filaments of dark gas and dust that is there, but what you have not seen is that the bright objects there are indeed clusters. So we can have many more clusters just looking at the brightness of the Gaia sky. What will happen in the further data releases? Gaia is going to improve our knowledge of all the known data clusters at a precision that is of the order of 1/10%, and we'll discover a new one. We are going to answer to basic questions like, are all our stars really born in cluster and then lost? Was our sun born in a cluster? Are all the clusters we see now in the disk born in our galaxy, or they came from outside? And how was our galaxy formed? And finally, I want to leave you with this beautiful Gaia sky that you have already seen, but with all the majority of the objects that are annotated there are clusters. And now it's time for the opening of the Gaia archive. So, thank you very much.
Antonella. Yes. Thank you very much, Antonella Valenari from the University of Padua, for this first example what we can do with the Gaia data that we have been just releasing now, already 5 minutes ago. And as all the others, sorry? Very good. So confirmation we are live, and now please go there, grab them, enjoy, do the science, because there will be much more examples than coming from all of you out there that along the lines what Antonella just showed. And with a second example, and that has to do something with distances, and as you know, they're really vast in the universe, but we are getting a handle on it. And I would like now to invite Gisella Clementini from the University of Bologna. She's also associated with ENAF, to let us understand what Gaia is contributing basically to the solid fundament that a distance ladder needs in order for us to understand how far the different objects in the sky are away from us. Please, Gisella.
Thank you, Marcus. I should say that it's very difficult for me to be here now because I'm so excited and I would like to be sitting on my desk, downloading Gaia data. So I will sort of rush through my presentation just to give you a flavor of what I would like to do with this data. And, it's just an example. Gaia and the distance scale. So that's the main concept I want to get you. And the first thing I have to say is that measuring distances in astronomy is a big task. It's a difficult task. We cannot use a ruler to measure distances because distances are big, are too far big for any direct measurement except from very locally. And that's what Gaia does, actually, and very well. So what astronomers do usually is to build a distance ladder, which is made of different methods and so-called distance indicators, from which you can go from very close by to increasingly large distances, but you have to find a way to link the different steps of the stairs, and you have to found your stairs on very good grounds. And the first step of the ladder is, in fact, the parallax measurement, which is the only direct and straightforward measurement of distance, which Gaia is doing already and will do much, much better than was done before. And that's to give you a flavor of that. You have here in the ladder the first step with the parallaxes as Hipparchus gave us, and how Gaia will expand our view. This is giving the idea of accurate, precise parallaxes. So basically, with Hipparchus, we could look precisely at, sort of backyard of the solar system in terms of distances, something like 300 light years. But with Gaia, we will peer into the garden of one of our close neighbors, the Large Magellanic Cloud, 200,000 light years away from us. Now, how do astronomers build this ladder and go from close by distances to the universe at large, let's say? The way the measurements are done is locally with parallax, and I don't need to tell you much more of that. Then, if you want to go to larger distances, astronomers define a concept that is the concept of standard candles. Standard candles are objects that we know the brightness, the intrinsic brightness, like the wattage in a bulb, but that we see fainter as they get closer, as they get at larger distances. That's basically for effect of the distance. So if we know the intrinsic brightness of these objects, when we see them fainter, we can infer the distance they are at. And so, in two ways that Gaia will dramatically improve our climbing of the cosmic distance ladder. First of all, through parallaxes, locally, and then through the calibration, the derivation of the accurate distances from standard candles. And in the first data release, there will be parallaxes for very special objects that I like a lot. Twinkling stars that by twinkling tell us how far they are, and these are the variable stars, objects that vary their brightness because they swell and shrink in a very regular and, I would say, and periodic way. And for these two kinds of objects specifically are very nice, the Cepheids and the Aurolaris, variable stars, because they follow in the variation of light a relation that is called the period luminosity relation that links how the brightness, the average brightness of these stars vary with the period, the time of a full variation. So what Gaia will do for us, and it's already doing for us, is to pin down this relation that we can use then to measure distances up to the way to Andromeda and much farther away, the external galaxies, and much farther away than locally. And just to give you an idea what is in the catalog that each of you can already download now, here is the content of Gaia first data release in terms of parallaxes, new parallaxes, for a small number of Cepheids and Aurolaris stars from which to calibrate this relation between luminosity and period. But these are the closest objects for which Gaia is measuring directly the parallax. So for those stars, Gaia is measuring with great accuracy, has started measuring and will measure the distance directly more and more accurately in the next release. And then also in the catalog, we are releasing today, we have some 3,000 Cepheids and Aurolaris in that small galaxy, dwarf galaxy, the large Magellanic Cloud, which Anthony showed a very nice view from Gaia. And this is a small sample, but already 12% of the sample are new discoveries by Gaia. So this is the kind of light curves, how the brightness of the objects we are releasing varies with time. So you have brightness on the y-axis and time on the the horizontal axis, the x-axis, and you have Cepheids on the left and Aurolaris on the right, and you can appreciate the quality. I should say that I'm not playing the game of removing errors here, but you cannot, the errors are inside the point, so that tells you the quality of the data. And this is in the LMC. So it's one of our closest neighbor, but it is, quite at a large distance from us. It's slightly less than 200,000 light years away from us. Now, this is the distribution of the Cepheids for which we are releasing parallaxes today. They are mainly concentrated on the galactic disk, which is normal. That's the place where they live, this kind of objects. These are massive young stars. And this is a distribution of the auralaris instead. They populate the halo of the galaxy, of our Milky Way, and the halos of galaxies in general. So, putting them together, we get a full view of the galaxy, of our galaxy. And then, just to give you a flavor of how good we are already doing with Gaia now, here I'm showing you this a very short or a very crude, if you want, image where I have plotted the brightness, the average brightness of the sample of satellites we have released today toward period, time variation. And this is according to Hipparchus parallaxes, and this is what we are getting with Gaia already in this first data release. So you see, this is in terms, so while, with Hipparchus, we couldn't really see a PL that well, now we see it. There is a clear relation there. And the same applies also for auralaris. These are a sample of, I think, 140 auralaris that we are releasing today, according to Hipparchus, and that's how Gaia give us an opportunity to look at the period luminosity relation of these objects. And now I want just to conclude that it's not only distance, but also structure of galaxies that we can infer from these objects that we are releasing today, these variable objects. And here I give you a flavor of what Gaia is doing now and promises to do in the future. This is a view of, again, the Large Magellanic Cloud, and the AUGL foreground-based survey has recently revealed a wealth of auralaris stars in that galaxy, the orange objects that trace the halo of that galaxy. But Gaia looked at the Large Magellanic Cloud as well, and here you have the green and red points. Those are the red ones, new Gaia discoveries. And so Gaia is already telling us that the Large Magellanic Cloud is much larger, much extended than we could have thought before. And the same is going to apply also for the Milky Way. And I conclude here just thanking you for your attention.
Thank you, Gisela. For this second example, what we can concretely do with the data. So we will learn a lot about the distances. And already I understand the Milky Way is bigger than we thought. The Magellanic Cloud is bigger than we thought. So there's, I think, a lot of real discoveries in there. And now we're coming to the different questions you may have here in the room. So we have a colleague over there with a microphone. Please feel free to ask. But if you ask, please give us also your name and your affiliation. And I'm having a look at the screen, whether there has been something from the internet. And if you still want to ask, use the hand.
Se volete un secondo, c'è l'archive aperto. Ve lo faccio vedere. Gaia Archive. Vediamo se si riesce a collegare. Eccolo qua, dovete andare su Search e c'è una pagina per le richieste molto basilari. L'oggetto che volete, quanto volete intorno, se lo volete il Gaia, cioè solo la fotometria, o se volete vedere se c'è qualche sorgente TIGA, se c'è, se sapete che se ha le parallassi, e vi verrà fuori intera set informazioni disponibili. Oppure potete andare sulla DQL form, dove avete degli esempi di quello che potete fare, e vi vengono fuori, avete la maniera per interrogare tutte le tabelle che sono all'interno di Gaia. Per esempio avete i cross match ai vari cataloghi, adesso non mi ricordo dentro come, il TOMAS è qua, SDSS, avete dentro tutti gli ID per fare i vari cross match. Non è una cosa semplice usare il catalogo di Gaia, ma c'è tutta la documentazione per aiutare. Sulla parte di visualizzazione sinceramente non mi ricordo cosa c'è, ma insomma non ho mai dato un'occhiata, ma probabilmente ci sono tutte le immagini che avete visto finora. Grazie ai sopravvissuti. So che è stata lunga, grazie per essere venuti. Penso che abbiamo fatto prima, se ci sono domande, semmai ce l'ho.
Grazie. Salutiamo quelli collegati che erano parecchi.
Grazie a tutti. È venuta bene.
Un paio di curiosità.